Hello and welcome to this ODE video specifically about exact ODEs. So every exact ODE shares the form m of xy, just a function of x and y, dx plus n of xy, different function of xy, dy equals 0. So this is the form of any exact ODE, but actually if an ODE is in this form, it's not necessarily exact. So there is one thing that you have to check just to make sure that you're actually working with an exact ODE and so that this method that I'll show you will work. And that's you need to take the partial derivative of m with respect to y, and then you need to make sure that that equals the partial derivative of n with respect to x. And so if this is true, then that means you're working with an exact ODE. And there's a sort of specific idea behind these ODEs, which I'll go into just a little bit here, maybe so it'll just make a little bit more sense. So your final answer of this kind of ODE is going to look like psi of xy equals c. And so this is just how they take care of the constant, because every sort of ODE or integral is just going to have some sort of a constant at the end, right? And you'll see that we do take a couple of integrals with this method. So this constant will make sense at the end, and it's convention to call your final answer psi of xy and to set that equal to the constant instead of saying psi plus c equals 0. So psi here is going to be the implicit version of the final answer. So it's not going to be y equals, or it's not going to be x equals, but rather it's going to be a function that involves both y and x, but neither of them are solved for. And so on a little bit of a deeper level, what it actually means to be an exact ODE is that m equals partial psi, partial x, and n equals partial psi, partial y. And so this is true for every given exact ODE, and of course our final answer is psi. So it may make sense why we're going to end up taking integrals here, right? Because if we got dx on this side, for example, then we could integrate everything. But that's just a quick little overview of exact ODEs in general. So we're going to go ahead and get into some examples here. Okay, with our first example, we're going to start with, how about, okay, here we go, 3x squared minus 3y squared dx plus 1 minus 6xy dy equals 0. And so right off the bat, this looks like it could be an exact ODE, right? We can see right here, this is what would be m, and this is what would be n, but we don't know for sure that it's exact yet, and the only way to make sure is to take partial m. Here, I'll actually keep this definition right here. So we need to make sure that partial m, partial y equals partial n, partial x. And so we're just going to find both of those derivatives. All right, so partial m, partial y equals, well, we're just taking a partial derivative, so it's just like any other derivative you've ever taken, except anything that's not a y, you totally ignore. You treat anything that's not y as a constant. In this case, there's really nothing different, so partial m, partial y is just going to be negative 6y, and that's from the power rule right here. And of course, we're treating x as a constant since this is a partial derivative. So the derivative of a constant, in this case 3x squared, is going to be 0. All right, now let's see, put a little question mark here. Does this equal partial n, partial x? So n's right here. Partial n, partial x, well, that's just going to be negative 6y. So we can tell that, yes, they are equal. And that derivative just comes from the 1 is constant and negative 6xy. We're treating y in this case as a constant. And so then we just basically lose the x when we take the derivative. All right, But we've made sure that it's exact, so now we actually need to solve for the implicit final solution of this ODE. So to do that, we're going to start with the idea that m equals partial psi partial x. And we know what m is, right? In this case, it's 3x squared minus 3y squared. And so what we can actually do here is solve for psi by taking a integral. So we can say, okay, that means that psi equals the integral of 3x squared minus 3y squared dx. This is just by rearranging the derivative here. This is actually kind of a separable ODE in itself, right? We want to get every psi on one side and every non-psi on the other side. And I say non-psi because typically the fact that there's an x and an y would matter here for a separable ODE. But remember, this is a partial derivative, and so anything that is not x in this case is going to be treated as a constant, and you'll see that in the integral. Okay, so all we need to do here is actually take this integral. So the integral of 3x squared dx is going to be x cubed, because there's going to be an over 3 here, and then we're going to add 1 to the power. So 3's would cancel, right? And then the power becomes 3. Now, as I said, we're treating y as a constant in this case, and so the integral of a constant is just that constant multiplied by the variable you're integrating. In this case, we're integrating with respect to x. So this is going to be our psi, but there's a little bit more of a difficult constant of integration here. And in fact, it doesn't need to be a constant because of the fact that this was a partial derivative up here. So remember that if you take the partial derivative of a function with respect to x, then anything that wasn't x totally disappears. So for example, partial sine of x, partial y, is just going to be 0. And so for that reason, we need to account for the fact that there could have been any function of y. Because if we were to take the partial derivative here with respect to x, then because c of y doesn't involve any x's, anything that it involved would just go to 0. So in this case, our constant of integration is actually a function of integration. And sort of the rest of the problem is just going to be finding what that function is. So this is what psi looks like. Our only unknown now is, okay, we need to make sure we have this in our final answer. So we actually have enough information to solve for c of y. And that's because, remember, n equals partial psi partial y. And so if we take the partial derivative of what we found to be psi with respect to y, we can compare it to what we know n is. So I'm going to draw a little arrow here. Let me move over a bit, and I'm going to say partial psi partial y equals, and then we're going to take this partial derivative. Now x cubed, that's going to go to 0. Negative 3y squared x is going to be negative 6xy. And then the derivative of a function of y is just simply that function's derivative. Okay, so now based off of the psi that we have created, we have partial psi partial y. But the problem tells us what n is at the very beginning. So n in this case is 1 minus 6xy. So n is 1 minus 6xy. So we have two different equations telling us what partial psi partial y should look like. So we can set them equal to each other. So 1 minus 6xy, let me write that a little bit better. 1 minus 6xy equals negative 6xy plus c prime of y. Okay, and so now we can just add a 6xy to both sides. These are going to end up canceling. And we can say c prime of y equals 1. Okay, so writing this in Leibniz notation, dc of y, it's a little bit confusing there, but that's a c and that's of y. And then dy equals 1. And remember, it's a derivative with respect to y because that's what originally initiated the prime. That's what made it a derivative in the first place. And so this is actually just a really, really simple separable ODE. So dc, I'll just remove the of y because we know it's a function of y, equals dy. And so simply we integrate both sides. So c equals the integral of dy is just y. So we have found that c actually did just equal y. And so there is a constant of integration here, but we're going to account for that in our final answer. So I'll show you that here. And actually now we have enough information to write our final answer. So remember what we said up above. We said that psi equaled x cubed minus 3y squared x plus c of y, but now we know what c of y is. We know that it's just y. So we can write a new psi equals, and let me go memorize that really quick, x cubed minus 3y squared x cubed minus 3y squared x, and then plus y. And then, as I said earlier, it's convention here to set it equal to the constant instead of adding it to this integral right here. And so this is the implicit version of the answer to the ODE. And 9 times out of 10, actually probably 99 times out of 100, if you're asked to solve an exact ODE, then they're only going to ask you to solve for the implicit final answer. Because, I mean, if you were to try and solve for x or y in this equation, you could see that, well, it may not even be possible depending on the ODE. So typically professors will just say, okay, solve for it implicitly because I'm not really testing your knowledge of cubics, I'm testing your knowledge of ODEs. Okay, but that was a really good example, and so every problem sort of follows that exact same formula. So let's just go ahead and get into another example. Okay, so I just went ahead and wrote it down already, just so you didn't have to watch me write that. So this, as we know, is going to be m, and this, as we know, is going to be n. And so the first thing that we always have to do is make sure that this is actually an exact ODE, so we know that the method works. So remember, we take the partial of n with respect to y, and we have to make sure that that equals the partial of n with respect to x. So let's start with partial m, partial y. All right, so this looks like it's going to be a product rule right off the bat. So first of all, this is going to be 2 terms. It's the product rule. So I'm going to start by taking the derivative of y. So this is going to in turn be 1 times e to the xy plus y times the derivative of e to the xy with respect to y. So that's just going to be x e to the xy, and then the 2x totally disappears because we treat x as a constant. Okay, so let's go ahead and make sure that partial n partial x is the same thing. Partial n partial x equals x e to the xy. Looks like another product rule. So I'll do the same thing. Let's land the derivative on x first. So this is just 1 times e to the xy plus, now the derivative is on e to the xy. So derivative of e to the xy with respect to x, always just write e to the xy, but we know that's going to be multiplied by x, and then in this case, derivative y e to the xy. Okay, so yeah, we have made sure that they're the exact same thing, and so nice, they're equal, so these are exact. Okay, we know they're exact, so we can go ahead and actually do the method. So remember, the first thing is that we have to remember that m just equals partial psi partial x. So let me write that here. M equals partial psi partial x, and in this case m is y e to the xy plus 2x. So y e to the xy plus 2x. Our goal here is psi, so we're going to integrate with respect to x to find it. Integral of y e to the xy plus 2x with respect to x. Okay, so this is going to be, let's see, y e to the xy. So this is going to be y times the integral of e to the xy, because we're treating y as a constant. The integral of e to the xy is just going to be 1 over y times e to the xy. So those y's will cancel and we'll just be left with e to the xy. And then plus x squared as the power increases by 1, and then we divide by that power. And then of course add our constant, which in this case could have been a function of y. All right, let's move forward and let's find out what this function is. And we can do that because we know n equals partial psi partial y. And in this case, n is xe to the xy plus 2y. xe to the xy plus 2y. Okay, so we're just going to take the partial psi partial y here in order to get it to match this equation right here. And so let's see what that gives us. That's going to give us, let's see, just I'll write it here. Or, oops, my bad. Partial psi partial y. So that derivative is going to look like, okay, taking the partial derivative with respect to y of e to the xy, we write down the exponential. Now it's the derivative of the exponent. Derivative of xy with respect to y is just x. So this is going to be x, and then plus c prime of y. Okay, so now we have two equations for partial psi partial y, and we can set them equal to each other. So xe to the xy plus 2y has to equal e, or I'll write the x out front, xe to the xy plus c prime of y. Okay, so let's subtract an xe to the xy from both sides. And then we are just left with c prime of y equals 2y. Now we can integrate, right? So we took a partial derivative with respect to y, so we have to integrate with respect to y. And so then c equals the integral of 2y dy, which is going to give us c equals y squared. Okay, so now we have psi. We have everything that we need. We finally figured out what c of y is, and now we can just put it together. So if you recall, our psi was e to the xy plus x squared, and now we know it's going to be plus y squared. So psi is then equal to e to the xy plus x squared plus y squared. And we didn't include the constant here because it's convention in ODE. You'll see this pretty much everywhere you see an exact ODE, is to set the implicit equation equal to that constant instead. All right, so then this is your implicit answer to the ODE. And again, solving for x or y here would be a nightmare and may not be possible. And so you're probably never going to be asked to solve for x or y explicitly. An implicit answer is almost always going to be the way to go here. Okay, so let's do another example. All right, here we go. Again, I already wrote it down, and I chose this one because it may not be immediately obvious that this is even in the form of a possible exact ODE. So when you see something like this, usually just write out what that prime actually means, and then maybe it'll be more clear what you're actually doing. So 2x plus y squared plus 2xy, and then that prime actually means dy dx equal 0. And then here, if we actually multiply both sides by dx, right over here, dx, then we're left with, let's see, 2x plus y squared dx plus 2xy dy equals 0. And you can see that, okay, well, this looks a little bit more familiar. This looks like it has the possibility to be an exact ODE. And so once you see that, all right, then you test, is it an exact ODE? So this is m, and in this case, this is going to be n. Okay, so we need to make sure that partial m partial y equals partial n partial x. So partial m partial y equals, well, so 2x, constant, derivative of a constant is 0, so this is just going to be 2y. And then we have to ask ourselves, what is the partial derivative of n with respect to x? And that's just going to be 2y as well. And that was partial n partial x. And so the answer here is yes, it is exact. And if you were to find that the partials weren't the same, then simply that's not an exact ODE and this method won't work. So you'll have to try something else. But we know for sure that this is exact because of this method, and so we can move forward and actually solve for the ODE here. Okay, so we know that partial psi partial x equals n, or in this case m, rather, sorry about that. And we know that m equals 2x plus y squared, as we have denoted here. Okay, so now we can just do what we have been doing, integrate with respect to x. So 2x plus y squared dx, and that's again because we're moving this differential here and then integrating both sides. Okay, so let's see what this integral is. Okay, so taking this integral, we're going to be left with, okay, let's see, 2x squared over 2 is just x squared. Then the integral of y squared with respect to x is just y squared x. And then we're going to add that function of y where it could have been anything. And so now our goal is to find out what c of y is. So we know that partial psi partial y equals n, which in this case is 2xy, as we have written up here. And so then, as long as we take a partial derivative of our psi and compare it to this, we'll know what c of y is. So this turns into partial psi, let me write that better, partial psi partial y equals, okay, let's see, 2xy plus c prime of y, just like that. All right, now we can compare the two that we know have to mean the same thing. So this means that 2xy equals 2xy plus c prime of y. And so if we were to subtract both sides, or 2xy from both sides, we would be given c prime of y equals 0. Integrate, or here I'll write that in a better way. C equals the integral of 0 dy, but of course this just equals 0, and remember we're going to write the constant later. So now we know that c was actually 0 the whole time, and we know immediately that psi is just x squared plus y squared x. So that means that our final answer is x squared plus y squared x, and then it's convention to set that equal to the constant instead of finding it here. And then that's going to be our final answer. And, you know, here we could have actually, you know, solved for y if we were asked to. We could have solved for x as well. So, you know, it's possible to be asked to solve for y or x, but I've never seen or heard of somebody tell me that their professor actually asked them to solve for this non-implicitly. All right, let's get into another example. All right, here we go, and this is another one where to recognize that this could be exact, again, we have to multiply both sides by dx. And so this would just give us 3xy plus y squared times dx plus x squared plus xy times dy. And then again, this is in the exact form that we want, where this is m and this is n. All right, so it is in the form of what could be an exact ODE, so now we just need to make sure that it is one. So we need to make sure that this statement is true. So we'll start just by finding partial m, partial y. And of course, m is right here, so partial y is just going to be 3x plus 2y. Okay, and then so what's partial n, partial x? Well, n is right here, so 2x plus, and then just y. So actually here, they're simply not the same. So, not the same. So partial m partial y does not equal partial n partial x. So not exact. And so at that point, well, maybe if your professor is just asking you to, if the ODE is exact, solve it, then you're done, and that's really nice, right? But if they want you to solve the ODE regardless, then you're going to have to try another method. This is not exact. All right, we'll go ahead and do another example. All right, here we go. So in this case, right off the bat, this is what could be m, and this is what could be n. So let's make sure it's exact. That last one wasn't, so it is possible, even if it's in this form. So partial m partial y, that's going to be just 0. And then we want to know, does that equal partial n partial x? And so in this case, partial n partial x is also 0. So we can write a little yes there, and we can be happy because now we know exactly how to solve this ODE. All right, so let's do the method then. So remember that partial psi partial x equals m, which equals 2x plus 3, which means move this differential to this side of the equation and then integrate both sides. And you have psi equals the integral of 2x plus 3 dx. Okay, so then this is not a half bad integral at all. 2x squared over 2 is just going to give us x squared, and then plus 3x plus c of y, some random function of y, if there is one. All right, also remember that partial psi partial y equals n. So this is how we move forward. In this case, n is 2y minus 2. So 2y minus 2. So we need to make sure that these equations look the same once we take the partial of what we found to be psi. So partial psi partial y is going to be, let's see, okay, the x squared just totally disappears, the 3x totally disappears as well, so this is just c prime of y. And that means that setting these two equations equal to each other, that c prime of y must equal 2y minus 2. So another way of writing c prime of y is dc of y dy. So we can write dc dy equals 2y minus 2. We can multiply both sides by dy. dc equals 2y minus 2 dy. Take the integral of both sides. That gives us c equals y squared minus 2y. Okay, so then we found c, and at that point you're pretty much good to go. Now you just write down the answer. So y, or psi, equals x squared plus 3x plus y squared minus 2y. What we already knew, and then what we just found. Okay, so we're going to set this equal to a constant to account for the fact that any of those integrals involved a constant of integration, and that's going to be our final answer. All right, here we go. This is another ODE that could be exact. It's in the right form, m dx plus n dy. So we can just mark this as what might be m and this as what might be n. And then we can take the partials and make sure they're equal to each other in order to confirm that it's exact. So the question is partial m over partial y, does that equal partial n over partial x? So let's see, partial m over partial y in this case is just going to be 4. And so does that equal partial n partial x? And so partial n partial x is just going to be 2. So no, they do not equal each other. So these are not equivalent, and therefore this equation is not exact. And hopefully that's the end of the problem for you, right? Hopefully your professor doesn't ask you to solve for it still. But this equation, or this ODE, is not exact, so obviously the exact ODE method won't work. All right, let's go ahead and do another example. All right, here we have another equation here, and maybe it's exact. First, we need to get it into the form of m dx plus n dy. And actually here, a, b, and c are just constants. All right, so let's just go ahead and rearrange this equation to maybe get it into the correct form. So let's just multiply both sides by dx, and we're left with negative ax plus by equals bx plus cy times dx. Now we'll multiply both sides by this denominator, and we'll get bx plus cy dy equals negative ax plus by dx, like that. And now we'll bring the x's, or the dx, onto the left side, and then we should have ax plus by dx plus bx plus cy dy equals 0. And then now it's clear that this could be exact, and that if so, this is m and this is n. So does partial m partial y equal partial n partial x? So let's start with partial m partial y, and so in this case, partial m partial y is just going to be b, and partial n, let me write that better, partial n partial x is just going to be, yep, just b. So they are in fact equal, and so this is an exact equation that we're working with here. All right, so now we actually solve the ODE. Partial psi partial x equals m, which equals ax plus by. All right, so this means that psi equals the integral of ax plus by dx, and so then psi equals 1/2 ax squared plus byx plus c, or just regular c of y, not the prime yet. Okay, so let's take the partial here, partial psi partial y. This equals just, let's see, just bx plus c prime of y, like that. Okay, now we know that partial psi partial y also equals n, which in this case equals bx plus cy. So bx plus cy. Set these two equal, gives us bx plus c prime of y equals bx plus cy. Okay, so I have called the function c of y, even though there's a c constant, so I'll keep referring to it as c of y to avoid confusion. This is a function and this is a constant. So we're going to subtract bx from both sides, and we'll get c prime of y equals cy. And so then that has to mean that c of y equals the integral of cy dy. So then c of y has to equal cy squared over 2. And I'll go ahead and, just because this is a function, not a constant, I'll go ahead and I'll rename this everywhere I see it C1, just because we don't want to be confusing. Okay. Just to make sure that it's clear to whoever's looking at this, the professor on an exam or whatever, that this is a different variable than what they defined as C. Okay, but we found the answer basically. We know what the unknown constant is, and we know what psi is. So 1/2 ax squared plus byx plus 1/2 cy squared. So this equals any type of constant that we might have run into during integration. And so then 1/2 ax squared plus byx plus 1/2 cy squared equals c is our final answer. All right, that's going to do it for this one. So let me know if you guys enjoyed, and let me know if you have any specific questions. Thank you very much, and good luck.